Hi everyone, this is Dr. Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in the previous sessions, we have discussed about various shear force and bending moment diagrams for various beams. So we have discussed about cantilever beam with the point load and cantilever beam with the UDL. Similarly, other beams, simply supported beam with the point load and UDL, and then UVL, uniformly varying load. And also we have discussed about this shear force and bending moment diagram for UDL with point load. So in this session, we will see some more shear for other beams, and also the relation between this shear force and the bending moment. So in this module, the CO2 is illustrated the shear force and the bending moment distribution in beams for analyzing the structural behavior under various loads. After completion of this module, the student be able to answer the what is the shear force and what do you mean by bending moment, and how to draw the shear force and bending moment he can do. So and also the student able to analyze the structural behavior under various loads. So different types of loads are there, point load, uniformly distributed load, and varying load. So for all these loads, whenever the beam is subjected to this type of loads, so what is the behavior of this beam? So the bending moment distribution, how it will distribute in the beams, and also the shear force diagrams. This is the main objective of this the course outcome. So in this session, I will explain about the shear force and bending moment diagrams for overhanging beams. The beams are classified into various types. One is cantilever beam, simply supported beam, and then overhanging beam, and fixed beams. So in this session, we will see the overhanging beam subjected to different loads, maybe point load or maybe UDL. So how to draw the shear force and bending moment diagram? If the end portion of the beam is extended behind the support, such a beam is known as overhanging beam. So already in definition, in first class, in introduction class, I have seen the overhanging beam main definition is when it is said to be the overhanging beam, if the end portion of the beam is extended beyond the support. Suppose the beam is like this, the end part is this one and another end is this one. Suppose A and B. So reaction forces. So in this, the end portion of the beam is extended beyond the support, beyond this support. These type of beams are called overhang. So it means here some portion overhanging. So this is L, and what is the overhanging? This is take X. The overhanging beam length is X. In case of overhanging beams, the bending moment is positive between the two supports, whereas the bending moment is negative for the overhanging portion. So in this case, the bending moment is positive between the two supports. In between these two, the bending moment is positive. So whereas the bending moment is negative for the overhanging portion, in this portion the bending moment is negative. Hence, at some point the bending moment is zero after changing its sign from positive to negative or vice versa. So at some point the bending moment is zero. So after changing its sign from positive to negative, whenever the bending moment sign it changes from positive to negative, there the bending moment is zero. So that point is known as the point of contraflexure or point of inflection. So we will see in the coming up slides. So in this, the point of contraflexure or point of inflection, that point is known as the particular point where it is happened. So the bending moment is zero. That is contraflexure or point of inflection. So the point of contraflexure, it is the point where the bending moment is zero after changing its sign from positive to negative or vice versa. Is the point where the bending moment is zero after changing its sign from positive to negative or vice versa. See in this, so the overhanging beam, see in this, it is one end support, that is A, and other end support is B. The type of load is UDL, 2 kN per meter. So length between these two supports is 4 meter. The overhanging portion is 2 meter. So in this, see here positive at RA and here 0, the bending moment, the shear force is 0. And also here it changes its shear force positive to negative at this B point. And then again the C, at the point there is no shear force. Similarly, the bending moment diagram also shown in for this given beam. So here up to this portion, the bending moment is the changes its positive to negative sign. So at this point is known as point of contraflexure or inflection. So it is the point where the bending moment is zero after changing its sign from positive to negative or negative to positive. So this is the example for this overhanging beam. See, what is the relations between load, shear force and bending moment? Load, shear force and bending moment. So in this figure, shows a beam carrying a uniformly distributed load, that is W, per meter unit length. Consider the equilibrium of the portion of the beam between sections 1 1 and 1 2 2. Here, the beam carrying a uniformly distributed load W per unit length. So consider the equilibrium of the portion of the beam between 1 1 and 2 2. This portion is at a distance of x from left support and is of length dx. See here, taken the section portion at a distance of x, that is length dx, and then the forces are acting on this. Which forces are acting here? See, one is F, the shear force at section 1 1. At 1 1 section, what is the force? Shear force. At this 1 1 section, upward direction. At this 2 2 section, F plus df, that is downward direction. And m plus dm is the moments, the bending moment at the section 1 1, and m plus dm bending moment at the section 2 2. The forces and moments acting on the length dx of the beam are the force F acting vertically up at the section 1 1. So the F is acting upwards, positive, and F plus df is acting downwards at section 2 2. Similarly, F plus df acting vertically downwards at section 2. What is this load? The load acting downwards, W into dx. So with the length dx, the portion is taken. Here, what is the load here? W into x, W into dx. This one is the load acting on the small portion. So total is at section x, the distance x, at section 1 1 is W into x. But taken a small portion, so that is W into dx. So that is load on the portion of the beam between 1 and 2. So the moments m and m plus dm acting at sections 1 1 and sections 2 2 respectively. So m plus dm, m plus dm and m acting at 1 1 and 2 2. In this, the portion of the beam of length dx is in equilibrium, hence resolving the forces acting on this part vertically. So here, resolving the forces, F minus upward forces, F minus F plus df, and minus the load is W into dx. W into dx is equal to 0. So F minus W into dx, F into dx minus F plus df is equal to 0. So expand this one. So F minus Wx minus F minus df is equal to 0. So get cancelled here for F. So the remaining one is W dx is equal to minus df. So here the df by dx is equal to minus W. So the differentiation of force, the forces acting on this spot vertically with respect to dx, x that is equal to W, the load per unit meter, unit length. So units are meter. So the above equation shows that the rate of change of shear force is equal to the rate of loading. So this one is the rate of change of shear force is equal to the rate of change of loading. So now regarding come to the bending moment, taking the moments of the forces and couples about the section 2 we get m plus m minus w dx into dx by 2 plus f dx is equal to m plus dm. So moments of the forces and couples. So here in the first part in selected part, this is the UDL w into dx. Why? Because that length is dx. Clear? So here force acting upwards. Another one is here F plus df acting downwards. So we can see here the diagram, and here movements in the clockwise and anti-clockwise m plus dm. Clockwise m and anti-clockwise so w for unit length, m plus dm. Clear? And downward m plus df. So now solid in previous equation we got after simplification of the equilibrium condition, the rate of change of force, shear force, is equal to the rate of loading occurred. So taking moments of the forces and couples about the section 2. So now in this you have to take in section 2. Clear? At section 2, you know the F plus df is the shear force at the section 2. M plus dm bending moment at the section 2. Clear? The F plus df force acting vertically downwards at the section 2, and the F is acting vertically up at the section 1. So the load W into dx acting downwards. So all these things we have discussed. Now apply moments, taking the moments of the forces. Now the clockwise moment m minus w into dx by 2, taking it section about the section 2 plus what are the forces acting here? F plus at the section 2 here force F plus dx here dx by 2 plus F multiply with dx. One is UDL W into dx by 2 half of the portion, and then second one is another force is F force. What is the momentum about the for this force? The momentum of this force is F into dx, right? And is equal to the momentum in anti-clockwise m plus dm. This is equal to m plus dm. Clear? So that minus w dx square by 2 plus f dx is equal to dm. So here the load, after simplification, get cancelled here, and then finally you got w into dx square by 2 plus f dx is equal to dm. So here, neglecting the higher powers of similar small quantities. So here power is 2. So neglect the high powers of small quantities. So the quantity dx is the small elemental length. So we have taken a very small portion between the sections 1 1 and 2 2. So here 1 1, 1 1 section and 2 2 section. So we can neglect. The way because it will get a very small values. So that the final one is f into dx is equal to dm. So you can write f is equal to dm by dx or dm by dx is equal to f. So it means the rate of change of bending moment is equal to the shear force at the section. So the rate of change of dm by dx is equal to shear force at that section. This one. So this is the relation between the load and then shear force and the bending moment. So these three involved in this shear force and bending moment diagrams. So types of loads already we have discussed: point load, UDL and UBL, and shear force also have calculated for different types of beams and bending moment. But the relation between these three are derived here. So the rate of change of bending moment is equal to the shear force at the section. So another one is the rate of change of, after resolving the forces, the rate of change of force, shear force, is equal to the load. So after this, the rate of change of shear force is equal to the rate of loading. So we can write here in first one, we have derived the rate of change of shear force df by dx is equal to, so that is rate of change of shear force is equal to the rate of loading W. After applying the movements, the rate of change of bending moment, the rate of change of bending moment is equal to the shear force at the section. Shear force at the section. So dm by dx is equal to f. Now you can see here. So here so df by dx. So d by dx of, so what is the f here? dm by dx. So now you can write here d square m by dx. So double derivative of momentum, bending moment gives rate of loading. df by d is equal to, you can say in another way, right? So similarly, here you can write like this. So this is in terms of bending moment, dou square m by dou x square is equal to minus w. So in this session, we have learned relations overhanging beam, the shear force and bending moment diagrams for overhanging beam. Already you have seen in this shear force diagram and the bending moment diagram. And relation between the load, shear force and the bending moment have derived. Here the relation between the load and the shear force bending moment we have derived through taking small elemental portion of the beam length dx with length dx between the two sections, that is 1 1 and 1 2. Already have discussed in this diagram 1 1 and 2 2 section. Clear? After resolving the forces, you got equations, relations, two relations. So like this, how to show the shear force bending moment diagrams for various beams, and that is and according to the type of loads. In problem solving, we will see the detailed problem solving for each and every beam. So for this PPT preparation, I have taken references as Ramamrutam, other name, and the title of the textbook is 10th of Materials, and Danpati Rai Publishing Company. So R.K. Rajput, the title of the book is 10th of Materials, Hedson and Co. And R.K. Bansal, a textbook of Strength of Materials, Lakshmi Publications, 4th edition 2009, that is 2009. You can take recent latest edition also. And R.S. Kurmi and Gupta. The title of the book is 10th of Materials. And publishers are Chand and Co. So these are the references I have taken for this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.